Crossing the violent English Channel via an underground tunnel has been one of mankind's greatest engineering dreams. This dream was fulfilled in 1989 after a massive tunneling and sophisticated railway work. However, this simple tunnel train method has a very big technical issue. Can you spot it? To understand it, let's look at an example. After pushing the train for some distance, the boy struggles to push it. The compressed spring is resisting the train. The solution? Remove a portion of the spring and magically reglue it. Now he can push the train again. Similar to the resistance offered by the spring, when a high-speed train passes through a tunnel, the air in front of the train gets compressed and creates high resistance against the train. The motion of the train would be extremely difficult if this compressed air wasn't taken care of. The solution, similar to the removal of the compressed spring, is to remove this compressed air. The key to managing the compressed air lies in 194 piston relief ducts. Digging out a lot of soil from under the seabed and connecting the UK with France might seem like a simple project. But to understand the reality, you have to look at a cross-section of the soil. What if the tunnel collapses due to the immense pressure from the water? Also, water could find its way through the faulted layers. After a detailed geological study, the engineers decided to drill through the chalk marl, which was ideal due to its low permeability and good stability. These detailed diagrams of the different layers of soil below the seabed were not available before the mid-1950s. To understand the nature of the seabed, engineers had to drill hundreds of boreholes into the seabed, and extensive geophysical surveys were conducted from the 1950s to the 1980s. Interestingly, Napoleon Bonaparte had conceived a plan to build a tunnel connecting France and England across the English Channel. The idea was first formally presented to Napoleon in 1802, during a brief period of peace between France and Britain. A tunnel for horse-drawn carriages, lit by oil lamps. Unfortunately, the war between Britain and France resumed in 1803, and the project was quickly abandoned. Now, it's time to introduce a robotic caterpillar, the tunnel boring machine. We will soon see why we call this machine a caterpillar. Please have a look at the cutter head of this machine. It has many robust cutting tools. You can also notice portholes on the cutter head. Hydraulic pistons ensure that the cutter head is pressed against the ground with high pressure. Then, the cutter head spins. The excavated material, or muck, will also spin initially, but it has no way to go but into the cutter head portholes. The muck will start to fill the mixing chamber. A screw conveyor located here transports the muck away. Remember, these pistons have a specific stroke length. Note that pushing the cutter head forward, breaking the rock, and removing the resulting muck all happen simultaneously. Once one stroke is completed, the machine has reached this position. The TBM then starts the assembly of the precast concrete rings. Once the assembly is done, the hydraulic pistons are fitted to these concrete rings, and the TBM starts the next cycle of boring and muck removal. The motion of this machine resembles that of a caterpillar, right? These giant machines could not be transported fully assembled. Instead, they were transported piece by piece and then assembled on site. The TBMs were manufactured by the Robbins Company and Kawasaki Heavy Industries. These large individual parts were assembled at the construction sites at Shakespeare Cliff near Dover in the UK and Sangatte in France. At both locations, massive underground caverns or large open-cut areas at the tunnel portals served as assembly halls. These launch chambers had to be large enough to accommodate the entire length of the TBM. What's happening inside the launch chamber is a work of precision and expertise. A skilled team of engineers and technicians worked together for several weeks to assemble one TBM. Once fully assembled and thoroughly tested, the TBM was ready to begin its long, slow journey under the English Channel, inching forward. The Channel Tunnel project required 3 such tunnels, 2 main tunnels and 1 service tunnel. We've already seen the piston relief valves between the main tunnels. Please have a look at these cross passages. For any maintenance work in a main tunnel, service personnel enter through the service tunnel and access it by walking through these cross passages. As we discussed earlier, the discovery of a consistent chalk layer was a huge relief for the engineers. The TBMs could easily penetrate through it, but look at the shape of this layer. The TBMs had to precisely pass through the layer and eventually meet in the middle without a significant offset. If the tunnels met with an offset, the project would have ended in a disaster. How could the TBMs maintain such a complicated course? Remember, satellite mapping like GPS won't work at such great depth. To achieve this, the engineers first had to create a path under the seabed with known coordinates. The tunnel access line the TBM had to follow strictly. This required the clever surveying techniques and laser guidance system of the Channel Tunnel. The primary surveying task was to create a unified grid system connecting the British and French coasts. Before any tunneling could begin, surveyors had to know the precise 3-dimensional relationship between the starting point in Folkestone, UK, and the starting point in Sangatte, France. On a clear day, you can see England from France. Surveyors initially used traditional triangulation techniques, creating a web of interlocking triangles across the English Channel. They measured angles from high points on the cliffs of Dover to points on the coast of Calais. However, the distance was too great for highly accurate direct measurement across the water. To bridge the channel with the required accuracy, they employed high-precision electromagnetic distance measurement instruments. These tools send out light or microwave beams to reflectors on the opposite coast to measure the distance with pinpoint accuracy. The advent of GPS further helped with surface surveying. It also confirmed their surveying measurements. On this known coordinate plane, the engineers could select a few points to create the initial baseline for the tunnel. Once the surface grid was locked in, it was time to take the surveying under the ocean. The technique for this task is called shaft plumbing. Shaft plumbing accurately transferred the surface-level survey coordinates down to the seabed. A specialized surveying instrument called a zenith plummet was set up with great precision directly over a known survey point at the top of the shaft. The instrument is designed to look perfectly straight up or down. This tube isolates the plummet from currents. For the Channel Tunnel, optical plummets were also used. At the bottom of the shaft, there is another plummet that looks perfectly straight up to align with the laser or wires coming down from the surface. Once this alignment is achieved, that spot at the bottom of the shaft becomes the new coordinate on the seabed. From the detailed geophysical survey, the engineers knew the depth of the chalk marl. Combining these 2 pieces of information, the engineers established the tunnel access with many known coordinates on it. Now, the only question was how to make the TBMs follow this tunnel axis. This is where one of the smartest techniques of the Channel Tunnel project came in, the laser guidance system for the TBMs. A laser theodolite was mounted in the tunnel behind the TBM. They also arranged a few control points on the tunnel wall. The coordinates of the theodolite and control points were known to the engineers. A photosensitive target was mounted on the frame of the TBM. Its position was also known. Suppose after moving forward a few meters to align with the tunnel axis, the TBM had to be steered like this. The control points were arranged such that the laser would fall exactly in the middle of the target point upon perfect alignment. Suppose the driver didn't steer that much while moving forward. This would obviously cause the laser to fall off center from the target. The computer in the driver's control cabin would immediately inform him about this error, and he could take remedial action. As the TBM moved forward, the laser station was periodically leapfrogged ahead with more recently established control points. This painstaking process ensured that the path never deviated from the master plan. Even though it was easy to drill chalk marl, The fissures inside this layer were dangerous. A tunnel collapse under heavy hydrostatic pressure would take human lives and also trap the TBMs forever. This was something the engineers could never afford to happen. The solution was to strengthen the soil before starting the drilling. Grouting was the best solution to strengthen the soil. The TBMs were equipped with the capability to drill probe holes forward from the tunnel face. These holes would extend a significant distance, 100 meters or even 250 meters ahead of the advancing TBM. If the probe drilling indicated unfavorable conditions, grout was injected through these probe holes. This would effectively consolidate the ground, reduce permeability, and strengthen the chalk layer before the TBM physically bored through it. Here's a brain teaser for you. The engineers drilled the service tunnel ahead of the main tunnels. Can you tell how they did the grouting for the main tunnels? This image illustrates everything. Since the service tunnel was already drilled, with these radial drills, grouting could be easily done for the main tunnel's drilling. Despite extensive geological surveys, the precise ground conditions beneath the English Channel could only be fully understood by direct excavation. By drilling the service tunnel first, the engineers mitigated the risk. This also made the grouting of the main tunnels much easier. With the help of these smart engineering techniques, both the TBMs proceeded on the right course. However, when they were 100 meters apart, both machines halted. Only one machine drilled forward. Why did the engineers do this? This technique is called soft docking. Operating both TBMs until their last meeting point was obviously not a safe method. Another issue was the possibility of a misalignment. The first step in soft docking was drilling a narrow 5-centimeter diameter probe from the English side to the French side. This task was successfully completed on October 30th, 1990. This confirmed that the alignments of the tunnels were correct, a huge relief for the engineers. After the probe's success, a small pilot tunnel was excavated by hand through the remaining distance. This allowed the historic handshake moment on December 1st, 1990, when British and French workers met for the first time deep beneath the English Channel. This handshake marked the first time a land connection existed between Great Britain and mainland Europe since the end of the last ice age. Finally, the French TBM was carefully driven forward to break through the remaining ground, completing the main service tunnel excavation, the final machine breakthrough. If you think this is the final geometry of the Channel Tunnel, you are wrong. In fact, the engineers went for a more complicated design. A design with 2 crossovers. Why did they do this? The crossovers effectively divide the 50.5-kilometer tunnel into 6 manageable sections. This allows for maintenance work to be carried out in one section of a tunnel while trains are diverted through the crossover to the other tunnel, enabling a significant portion of the system to remain operational. In the event of an incident or obstruction in one of the running tunnels, the crossovers allow for traffic to be rerouted, minimizing disruption to services. You might have seen these large axial fans at the Shakespeare Cliff of the Channel Tunnel. What are they for? They are for the tunnel's fresh air supply. Fresh air is supplied to the service tunnel at both ends of the tunnel. The service tunnel is maintained at a higher air pressure than the main tunnels. This fresh air then flows into the main running tunnels through controlled louvers and doors in the cross passages. The cross passages connect the service tunnel to the main running tunnels at regular intervals, every 375 meters. These passages are equipped with doors that can be opened and closed to control airflow. A total of 11 TBMs were used for this project, 5 from the French side and 6 from the English side. Theoretically, 6 TBMs were sufficient for this project. The reason for using 5 extra TBMs was due to the different geological conditions. The geology on land, between the coast and the tunnel starting points, was different and more complex than the deep-sea chalk. It was unfeasible to try and use the same TBMs for these sections. For the land tunneling, 3 different TBMs were used on the UK side and 2 on the French side. Surprisingly, 2 out of the 11 machines committed a complete suicide. What I mean is that intentionally driving them into a rock and buried, a procedure often referred to as a TBM burial. Both of them were British TBMs. TBMs cannot move backward. It was a difficult and costly affair to dismantle and transport these machines from such a great distance. The 5 land-based TBMs were completely dismantled and removed. The remaining 4 were dismantled and partially removed. More specifically, their most valuable components were salvaged. Have you noticed these pipes inside the tunnel? What are they for? The trains generate heat due to air friction. For trains in the open, this heat is dissipated easily. But for the trains inside the tunnel, there is nowhere for the heat to go. If this heat accumulates, the high temperatures can even cause mechanical problems with the system. These pipes carry chilled water, and they continuously absorb the heat. This way, the engineers are able to maintain a safe temperature of 25 degrees Celsius. Let's take a virtual train journey through the Channel Tunnel and understand this marvel of engineering in greater detail. The train enters the Channel Tunnel on the French side at Coquelles. This location is approximately 6 kilometers inland from the English Channel coast. You may feel like the train is traveling straight, but in reality, the train follows a complex path through the chalk marl layer. We have already seen the use of piston relief ducts. You will encounter the first rail crossover after traveling 12 kilometers from the tunnel entrance. This region is, in fact, a massive undersea cavern. Suppose your train unfortunately encounters a technical problem. Thanks to the 2 crossovers which divide the tunnel into 6 sections, Channel Tunnel service will still continue. At this point, this specialized maintenance vehicle enters the tunnel. The robust gate in the service tunnel opens. Via these cross passages, the maintenance personnel can enter the running tunnel. Please note that the pressure inside the service tunnel is maintained higher than that of the main tunnel. In case of a fire in the running tunnel, this higher pressure will make sure that smoke and fire won't spread to the service tunnel. Thus, it will also act as a safe evacuation route. After the repair work, the train resumes its journey. The train exits the Channel Tunnel at Folkestone in Kent, on the English side, and eventually reaches the UK terminal. To start the next service, the train has to turn around. The train is then ready for its return service to France.
We've worked on the Channel Tunnel project for more than 4 months. If you are impressed with this content, please subscribe. And if you truly want to support my educational activities, please check out my Patreon page and pledge your support today. Take care. Bye-bye.